This is section 11.1, part 1. Today we're going to talk about sketching parametric curves. And I'll tell you what a parametric curve is in a minute, but first we need to do a short review of ellipses and hyperbolas. So if you have an equation that looks like this, both x is squared and y is squared, and there's a plus sign, and there's a 1 over here, you have an ellipse. And the ellipse is either going to be oriented on the x-axis, it's lying down, or oriented on the y-axis, it's standing up. And the quickest way to figure out what your ellipse looks like is to plot the intercepts. So for example, if we want to plot this ellipse right here, if we set y equal to 0, we're going to get the x-intercepts. So that'll give us x squared over 25 is 1. So x squared is 25. All right, well, if x squared is 25, then x is plus or minus 5. So those are the x-intercepts. And now if we set x equal to 0, then y squared over 4 is 1, so y squared is 4. So y is plus or minus 2. So our ellipse looks like this. When y is 0, x is 5 or negative 5. And when x is 0, y is 2 or negative 2. So our ellipse is oriented on the x-axis. And that's pretty much all you need to know to make a rough sketch. Now, of course, if a squared is equal to b squared, so let me come up here, if you have something like x squared over 25 plus y squared over 25 equals 1, then you have a special kind of ellipse, which is a circle. That's x squared plus y squared is 25. That would be a circle of radius 5, because it looks like x squared plus y squared equals r squared. All right. The equation for a hyperbola is very similar to the equation for an ellipse, except there's a minus. Okay? And depending on whether the minus is in front of the y squared or the x squared, your hyperbola is either going to open up and down, like this, or left and right, like this. And again, I think the quickest way to figure out which is just plot the intercepts. So in my example here, I've got x squared over 25 minus y squared over 4 equals 1. If y equals 0, then x squared over 25 is 1, so x squared is 25, so x is plus or minus 5. Now watch what happens if I try and set x equal to 0. If x equals 0, I get negative y squared over 4 is 1. So y squared is negative, let me move this over here. Y squared is negative 4. That can't happen, not in the real numbers. So I can't set x equal to 0. So if x is not ever 0, then I couldn't possibly have this picture. I must have this picture. So let's plot these points. When y is 0, x is plus or minus 5. Your hyperbola has to go like that. So you're going to need to make sketches of ellipses and hyperbolas today, so that will hopefully that will help you. All right, what's a parametric curve? A parametric curve is a curve that's described with a parameter, and we usually use t as the parameter. And so think of it as a curve on steroids. We're going to see in a minute that this parametric curve is actually the curve x equals y squared minus 4. 4y squared minus 4. So This is called a Cartesian equation because it's in x and y only, and there's no t. All right, so that describes a parabola that looks like that. The advantage of having a parametric curve like the one we have here is that you can describe a direction. As t goes from 0 to infinity, you can say, oh, I want to follow this curve, but in a certain direction. And if you don't want all of the curve, you can make restrictions on t, like saying, oh, I just want t to be greater than or equal to 0. So we'll talk about, in a minute, how to go from a parametric curve to a Cartesian curve. But right now, let's just look at how to plot a parametric curve. The most naive way, and often the easiest way, is just to plot some points. For example, let's just pick some values of t. When t is, oh, there's one other thing I wanted to mention before I plot this curve. A parametric curve can be written with one equal sign like this, and there's either parentheses or brackets around the x and y. So this is actually two equations. This is telling us that x is t squared minus 4, and then the blue is telling us that y is t over 2. So I have it color coordinated. You've got red and you've got blue. And both descriptions are fine. Sometimes I'll use two equations, like this is x, this is y, and sometimes I'll use one equation with parentheses and give both x and y. And your book will do the same thing too. So I'll try and do both notations today so you get used to both. All right, so here I have a little table. Here's x, here's y, and here's t. If t is 0, then x is negative 4 and y is 0. So that's right here. This corresponds to t equals 0. That's my starting point. All right, and then if t is maybe 2, then x would be 0 and y would be 1. And that's this point here. And so I know I'm going in this direction because as t increases, I'm going from that first point to the second point. And then I plotted a third point there, 12, 2, but I really didn't need to. Just 2 points will tell me what direction I'm going in. Plotting points isn't always going to work, plus it's a little bit slow. So another way to plot a parametric curve, a great way, is to use some technology. Desmos plots parametric curves. For example, doing this table method might be very, very difficult for this equation. X is cosh t and y is sinh t. T goes from negative pi to pi. So let me just switch to Desmos and show you how to do that. The way to tell Desmos you want a parametric curve is to use parentheses and put in x and y. So cosh t, and then a comma, sinh t, and then automatically the domain will come up. It'll tell you t goes between where and where, and you can fill these in. We want negative pi to pi. And I'm just typing in pi to get pi. So here's my parametric curve. And we'll see later that that's actually one branch of a hyperbola. All right, back to our video. Another way to sketch a parametric curve, which we're going to spend a lot of, in fact, that's the whole really topic of today's lecture, is how to eliminate the parameter to sketch the parametric curve. And there's three methods. If the equations are simple and algebraic, like this example we just looked at above, the parabola, solve one equation for t and plug that into the second equation. Doesn't matter which one you choose, I usually choose the easier equation. If you have trig functions, then use one of these identities. They're the Pythagorean identities. And method 3 is like method 1, but a little bit more creative. And I'll do an example of each one. I know method 3 sounds a little bit vague. All right, so here's the parametric equation that we plotted above, but now we're going to plot it by eliminating the parameter. That means get rid of t. All right, so we've got two equations. X is t squared minus 4, and y is t over 2. If I want to solve for t, I think the easier equation to use would be this one. So this one tells me that t is 2y. Okay, so I've solved one equation. By the way, this is method 1 above. I solved one equation for t, and then I'm supposed to plug it in to the other equation. So x is t squared minus 4, but t is 2y. So 2y squared minus 4. So x is 4y squared minus 4. There's my Cartesian equation. No t's. I know that's a parabola, and I know it opens sideways because it's x equals y squared, not y equals x squared. So also I know that when y is 0, x is negative 4. So I'm going to dot in that parabola. This is negative 4. That's the whole Cartesian parabola. However, the directions say sketch the whole curve with a dotted line, and then, well, I think there's some missing words here. Sketch the whole curve with a dotted line and portion of the curve, no, it's okay, and portion of the curve defined by the parametric equations with a solid line. So what's the portion of the curve defined by the parametric equations? That's when I need to look at the restrictions on t. T can only be greater than or equal to 0. So let's find out where we're starting. When t equals 0, now I'm looking at this equation. X and y are, let's set t equal to 0, you get negative 4, 0. So that means I'm starting here. Now, I'm either going to go up or I'm going to go down. Well, t is greater than or equal to 0, so pick a number to plot that's bigger than 0, because that's the direction we're going in. Maybe t equal, if I put t equal 1 in, I'll get fractions, so I'm going to put t equal 2 in. You get xy is 0, comma, 1. So now I have enough information to know I'm only getting the top of the parabola and I'm going in that direction. If t were allowed to be negative, then I could get this part of the curve down here, but t is not allowed to be negative. That's all I have to do. Okay, next one. This is another way you can describe a parametric curve. You can use pointy brackets. Some textbooks use pointy brackets instead of round brackets. Don't do that on Desmos though, because Desmos needs round parentheses. All right, pause the video and try this one yourself. I'm going to pause it too and fill some stuff in while you're gone, and then I'll explain things when we get back. All right, so while you were gone, I wrote down the two equations, x and y. I think in this case, the easier one to solve for t is the first equation. So I solved for t and got t is x over 3, and then I plugged that into the second equation. So I have a parabola again, y equals x squared over 9 plus 1. That's a parabola. It opens up and it passes through 1 on the y-axis. Now, to figure out how much of that parabola I'm getting, I look at the restrictions on t. If t is 1, that's my starting point, then x and y is, I go to my equations, x is going to be 3, and y is going to be 1 squared plus 1 is 2. So I'm starting here at 3, comma 2. All right, and now I need a number bigger than 1 to figure out which direction I'm going in. Let's go maybe t equal 2. xy is 6, 5. So I'm going that way. and that's the portion of the curve I get. Okay, now let's do a method 2. Because for this parametric curve, solving one equation for t and plugging into the other is going to result in a mess, because I'll have like inverse cosine, and then I'll have sine of inverse cosine. And so it's much easier to use method 2. So we've got x is 5 cos t and y is sine t. Solve each of those equations for cosine and sine. So the first equation tells me cosine t is x over 5. And the second equation tells me sine t is y. Now square both sides. I want to square both sides because I want to use the fact that cosine squared plus sine squared is 1. So cosine squared is x squared over 25, and sine squared is y squared. So instead of, in this equation here, instead of cosine squared, I'm going to put x squared over 25. And instead of sine squared, I'll put y squared. There we go. There's your Cartesian equation. And that's an ellipse. So to figure out what it looks like, when y is 0, x is plus or minus 5. And if x is 0, y is plus or minus 1. So it's an ellipse, and it's lying, it's oriented on the x-axis. This is 1 up here, and this is 5 here. Okay, so now we want to know how much of that ellipse we're getting if t goes from 0 to pi. So we'll plug in t equals 0, and we'll plug in t equals pi. If t is 0, xy is, going back to the two equations, cosine 0 is 1, so x would be 5, and sine of 0 is 0. So 5, 0 is our starting point. Our ending point is at t equal pi. That's going to give us xy equal, let's see, cosine pi is -1, so -5. Sine pi is 0. So this is our ending point. Now, there are two ways to get from that first point to the second point. One way would be the top root, and the other way would be the bottom root. Excuse me. If you're not sure, it's actually going to be the top root, but if you're not sure, plug in an intermediate value between 0 and pi, maybe t equal pi over 2, and see if you get a point on the top or on the bottom of that ellipse. So when t is pi over 2, xy would be cosine of pi over 2 is 0, sine of pi over 2 is 1. So we're up here. So that's how I knew I was getting the top half. Okay, pause the video and try this one. All right, I'm back. So I took the two equations, x and y, and I solved the first one for cos 2t, and I solved the second one for sine 2t. Cosine squared of 2t plus sine squared 2t is 1. And so I just replaced cosine squared 2t with x squared over 9, and I replaced sine squared 2t with y squared over 9. Now, that is an ellipse, but it's a special ellipse because a squared is equal to b squared. That's just a circle of radius 3. So let's plot that with dotted line. And let's see how much of that circle we're getting. So we'll go to the restrictions on t. If t is pi, if t is pi over 2, then xy is, okay, got to put pi over 2 in for t. So that would be cosine of pi, which is -1, times 3. So -3. And then we're going to get 0. All right. And then when t is pi, xy is cos 2 pi is 1, so 3, and then 0. So we're starting here. That's at t equal pi over 2. And we're ending here. That's at t equal pi. And to figure out whether we're going across the top or the bottom, we would pick a number between pi over 2 and pi. Maybe 3 pi over 4. And we get x comma y equals, all right, so 3 pi over 4, if I multiply by 2, I get 3 pi over 2. Cosine of 3 pi over 2 is 0. Sine of 3 pi over 2 is negative 1, so this will give us negative 3. So we're going this way. So we get the bottom of that circle. All right, one more of these. This is still method 2, and then we'll switch to method 3. This one's got secant and tangent, so we want to use the equation 1 plus tangent squared t is secant squared t. And I already went ahead and solved the first equation for secant and the second for tangent. So this tells me that secant squared t is x squared. And this one tells me that tangent squared t is y squared over 4. So when I plug in, I get 1 plus y squared over 4 is x squared. Now, to figure out whether this is going to be an ellipse or a hyperbola, we want to get the 1 on one side, positive 1 on one side, and both the x squared and the y squared on the other side. So this is, I can rewrite this as 1 equals x squared minus y squared over 4. Since there's a minus in it, I have a hyperbola. And so if I try and set x equal to 0, I'm going to see that I can't do that because y squared would be negative. So when y is equal to 0, I get x is plus or minus 1. So I know my hyperbola opens like this, left and right, going through 1 and negative 1 on the x-axis. And now I want to look at the restrictions on t. When t is 0, x, y is, secant of 0 is 1, so negative 1. Tangent of 0 is 0. So I'm over here on this branch. Now, I can either go up or I can go down. You look at the restrictions on t here. T is strictly less than pi over 2. And that's because tangent of pi over 2 isn't even defined. So to figure out which direction I'm going, I'm going to pick a number less than pi over 2 but bigger than 0, like pi over 4. In this case, I get x, y is, okay, secant of pi over 4 is root 2, so I'll have negative root 2. Tangent of pi over 4 is 1. 1 times 2 is 2. So y is positive and x is negative. I'm going in this direction because that point would be somewhere here, negative root 2, comma 2. So I'm getting a quarter of the hyperbola. All right, hang in there. I know this is a long video, and this is only half of it. We're on to method 3. So I'm going to do one example, you're going to do one, and then I've got a solved one here, and so we'll just be done after these next two examples. All right, so I've got two equations. X is 2e to the t, and y is 3 plus e to the t. instead of solving for t, I can see they both have an e to the t in them. So I'm going to just solve this one, not for t, but for e to the t. E to the t is x over 2. And then, you know, I could solve for t. I could take natural log of both sides and then plug it into this second equation. But why do that? I can just, I see there's an e to the t in my second equation, and I can just replace that e to the t with x over 2. Bam! I've got a line. I've got a line with slope 1/2 that passes through y equals 3 on the x-axis. So it's going to look something like this. This is, that point is 0, 3. All right, how much of that line am I getting? Let's look at t. When t is 0, x, y is, so I'm going up here, I'm putting in 0, e to 0 is 1, so 2 comma, and then 4. So I'm about here, 2 comma 4. This is my start. And now to figure out whether I'm going left or right, pick a number bigger than 0. Now I could pick 1, but then I'll have e's in my coordinates. So I'm gonna pick something like ln2. ln2 is bigger than 0, and so x comma y is 2e to the ln2 3 plus e to the ln2, which is e to the ln2 is 2. 2 times 2 is 4. And then when t is, oh, so this one, sorry, I was spacing out. E to the ln2 is 2. 2 plus 3 is 5. So 4 comma 5, I'm going in this direction. All right, so pause the video and give this one a shot. All right, I'm back. We've got two equations, x and y. I decided to solve the first equation, not for t, but just for ln t. ln t is x minus 3, and then I see I can just plug that into the second equation. And in place of ln t, I put x minus 3. You need parentheses because you have to distribute that minus. So we get, again, a line, y equals 4 minus x. So that's a line with slope -1 that goes through 4 on the y-axis. Okay, let's see how much of that line we're getting. We're starting at t equal 1. So when t equals 1, x and y equal, ln of 1 is 0, so 3 comma 1. So we're starting here at 3 comma 1. Now I want a number bigger than 1 to plug in so I can plot it, and I want actually a number I can plot, so I'm going to choose e. E is bigger than 1, it's about 2.7, and so then I'll get xy is 3 plus ln e. ln e is 1, so 3 plus ln e is 4, and then the y will be 1 minus 1 is 0. So that's here. So I'm going in this direction. Okay, here's a practice problem for you. You can do it, just be careful. You can't use cosine squared plus sine squared is 1 because this argument is t and this one's 2t. So my hint is use the double angle formula. All right, and try and do it without looking at the solution. In the next video, we're going to go in the opposite direction. We're going to start with a parametric curve like this, and we're going to figure out how to parameterize it. So we'll be going from here to here rather than from a parametric curve to a Cartesian equation. All right, I'm going to end the video.